Welcome to tutorial for Mac 0074. We're going to be looking at Workbench applied to looking at the modal analysis of this particular configuration. And so we've got here, if we have a little look, we've got a geometry of a piping system. So the idea is in this tutorial is we're going to draw this piping network, and then we're going to go through the process of putting in a mesh and then doing a modal analysis. And so we'll try and go through all of those parts of the calculation. Now just a kind of reminder, let's just have a look, see those numbers. This is going to be a pipe that's going to have, let's just make a note of those numbers. The internal, this is going to be, I think, DN800. Internal. Here we go. So we're given the density of the steel, we're given the internal and external diameter. So we're given an external diameter of 813 millimeters, and internal, so that's external. Internal is going to be 793.94 millimeters. This is going to be steel. Density of steel is 7850 kilograms per meters minus 3. Now we're going to be doing a modal analysis, so we're going to have to take into account the fact of water. Sorry, not water, of LNG. And so we're going to have to change this density of steel to make it effective density. So that's got to basically be the mass of steel plus the mass of LNG divided by the area of steel, and that's how we're going to get our effective density of the material. So let's just have a little look at this. And so the mass of steel is going to be rho steel is going to be pi d external squared d internal squared divided by 4 plus rho of that LNG of pi d internal squared over 4 divided by area of steel, which is dE cubed minus d naught squared pi over 4. And if we do the bit of algebra, then this is going to be rho steel plus rho LNG times di squared over dE squared minus di squared. We'll just have to work out that for the moment. Let's just have a little look, see what that is from our calculator. So let's sort of see. So let's go to MATLAB. Second, rho S plus rho LNG di cubed over d. Slide and add that later. Okay, so now let's look at the geometry of this, just so we've been taking a pipe which is 20 meters long, and we've got a 10 meter section, 10 meter section, and a 15 meter section, and a 10, and then 20 meters. So that's what we're going to draw now. Let's go through ANSYS. ANSYS is relatively straightforward. What I would advise, and always do, you could just do the modal analysis bit, put that in, and we can go to the engineering data and see what we have here. So we've got in here, we've got the correct Young's modulus, we've got the correct Poisson ratio, but our effective density is going to be quite different than this. And so we need to do a calculation there. MATLAB, and what did we say? We said that we've got steel. So we've got row S equals 7850. We've got D external being 813. We've got D internal being 739.94, and we've got row LNG equals to I've got it right somewhere, which is 455. Yeah, and so row effective is basically row steel plus row LNG times DI squared divided by DE squared minus DI squared. Oh, you can see no subscript. I'm being silly. And so this is a value of 1, 2, 1, 4, 7, 2. And so the reason why this is much larger than the close to 8,000 kilograms per meter cubed is because obviously it's a thin wall pipe and most of the area is actually taken up by the density of the LNG. Let's go back and put this in. The value I get is 17214. So ANSYS work 1, example 1. So let's just go back. Let's go to the geometry now. So this will open the SpaceClaim. There we go. Okay, so this is relatively straightforward. Just remember that you're dealing with meters. So you tend to work in millimeters in this case, and so what we've drawn out, and let's just remind ourselves about that, is on here is that we've got 20 meters, 10 meters, 10, 15, 10, 10, 20. Yeah, so let's draw those in first. Doesn't matter where we start. We're going to do now 20 meters is 20,000 millimeters. Yeah, and then we've got another 10,000. Oh, let's get rid of that. Got another 10,000, and then another 15,000, 10,000, another 10,000, another 20,000. Okay, and so that's our network. Now we want to do is want to put in a bend, and our bend is going to be, I think I've written it in there, is going to be 1.4 meters. So let's have a see. 1.4 meters is 1400 millimeters, and then same here, 1400 millimeters, and 1400 millimeters, and here 1400 millimeters. So that kind of gets our geometry. Let's just rotate that over here. Now they're probably wondering why do we have a joint in the middle? Well, this is because this is where we're going to put one of our constraints for geometry. Now let's obviously, what do we do next? Now the next thing is obviously we need to go to putting in a profile, and the profile we're going to put in is a circular pipe, and the challenge obviously I've got in here, which is a bit more difficult, is that actually I can't see it in my menu. You'll have greater success, I think. So this tells us the diameter, and what we've said, the outside is going to be 813, and then the inside is going to be 793.94. And so that kind of finishes off our internal geometry. Let's go back to our design. And so what we want to do is we just want to collect everything together. Let's go back to display, select, select, select everything and make it a pipe. And so there we are, that's the pipe. We've got everything connected together. Usually you've just got to make sure it's all shared. Be okay. We'll see if there are issues. We'll see them later on. Later, maybe I've made a mistake there. So let's go back to design. So we've done this. So exit SpaceClaim, go back to the workbench. Let's go set up the model. So here we're going to try and do the modal analysis. Okay, brings it in. Yeah, so I think I made a little error here. I've got two nodes here. It's a bit silly. I'll have to go back. So let me just continue this, and then I'll just show you an updated version of this. Okay, so the main challenge here is you can put in the mesh. So you can generate a mesh, just right click. Not very good, so what we do is we kind of add an insert sizing, and element size maybe 0.02 meters, so quite big. Fine mesh, update the mesh. You need to choose the geometry, obviously we just choose everything. Let's choose the line points that we get from here. Apply. Update. Very straightforward mesh, quite fine. Okay, now we've got to do the modal analysis. Now what we want to do here is we want to constrain the ends to be fixed, and then we want to put lateral constraints. So you look at the geometry in here. So one of the discussions that you'll have to look at will be to see putting in lateral constraints. So what we probably want here is not this node here. This we're going to fix. Actually, let's just put in the boundary condition here. Insert, fix support. Let's choose the fact that it's a point. So click this, go to the end, and go to the end. Apply. So they are support. And then I always get a bit anxious that it's actually chosen it. Oh, 2 vertices, that's pretty okay. And the next one is insert boundary condition of displacement, and what we want to do is we want to make the displacement on these two able to move in the x direction but not in the y or the z. So what we're going to do is x is free, y is fixed, constant, and then that's going to be our boundary condition. So let's just solve this, see if it gives us sensible results. Let's have a look at the solution. So if we're looking at the analysis, we do have a choice of the number of modes. Usually we put probably about. Now there is an issue to do with, and then we go back and then we solve again. We can look at the solutions in a kind of tabular basis. Now I'll just give you an idea. Some of these results are quite are repeated, and so that number 8 and 9 are quite similar, and 6 and 7 are quite similar, and so you have to be quite careful that some of these are kind of repeated routes. You have to realise how it's actually solved using power method you learned in year 2. What you really want to do is you want to figure out what the modes look like, and so here we go. So we should be able to produce the create, right click, create mode shapes. So it's moving a bit, so we'll go back to this, evaluate results. And so as we go through and have a look at the results, let's look at the lowest mode in this particular case. We go back to the graph, go to the lowest mode, graph, tabular data, the lowest mode, okay, so mode 0, let's have a look at the graph, the tabular data, mode 0 is the lowest. Let's have a look what that looks like, and you see the lowest mode is going to be the lateral displacement, you see, which is not unexpected. What concerns me is that the boundary condition on the fixed support is not there on the displacement. So the displacement, it's on one vertex. This is what I really don't like with the displacement. Let's remove that displacement, delete. Always check that the boundary conditions are inserted properly. Displacement, put it on this mode here. This is free, this is 0, constant, constant, and apply. Do the same with the other side, insert displacement over here. This is free, y is constant, z is constant, selection, apply, apply. And then what we do, we go back and recalculate, solve. When you do the displacements on fixed boundary conditions, I wouldn't try to group them together, I would do them one at a time because I always get kind of lost. It's not very good at kind of flagging up whether there are multiple boundary conditions applied. So let's go to the 0 displacement, so the lowest mode, we look at that. And now it's a bit more sensible, yeah, backwards and forwards movement. Look at the second mode, you start to see other modes are kind of creeping in. So remember, the displacement in the center that we have here is fixed, and so it doesn't preclude the thing vibrating up and down. Now, in order for you to kind of test boundary conditions or these kind of things, then you really need to kind of look to see how those values change as you change the mesh size. So we go to here, you see the lowest one, if you notice, are 0.6675. If I go to my mesh and go to the edge size and change that to something ridiculous like 0.5, and you'll see that I've got to update the mesh, solve, and then what you see is we do get a different answer, and it's going to be quite different. We'll choose a very coarse mesh, coarse mesh, but it's not far off, 0.66. So modal analysis are quite weakly dependent on size, but I chose a kind of ridiculous mesh and I'm getting quite similar results, but the ones later on are quite different. So what you need to do is to have some confidence to go through and systematically change the mesh size. Now, just one thing, I've rushed this, as you see, and what I've got is this double node here. So actually, you need to be a bit more careful when you do your geometry, so it is consistent with the size that we've got here. You to do, be a bit more careful than I have. I needed weep up here, so we said this is probably 17214, 241 kilograms per meters minus 3. Kind of points out that the density of the liquid has an enormous influence on the, or can have an enormous influence on the density of the system, the mass per unit length. Obviously, it has no effect on the stiffness, so the stiffness is unchanged in all of this. Kind of the part B bit, modal analysis. So I've shown you the modal analysis of an expansion loop, and I've set up these take to draw, so I should be relatively straightforward. So yeah, so let's just see what else do you need to do. Modal analysis of expansion loop filled with LNG. Note the location of fixed joints and lateral constraints. You need to decide and justify a choice of constraints right here. So I'm not saying that the lateral constraints are necessarily applied, but you need to go through and decide from your part 1, part A with the essay bit or discussion bit about what the